Hi guys, and welcome to this quick discussion for the midterm. Some of you have asked me to basically go through the problems. I sent you guys a solution, so hopefully you have had a chance to go through it. I know it's kind of brief, the one I sent. I did not really go in detail like typically I do when we solve problems together and things like that. But if in case you still have questions, I know that some of you asked about problem 3 because problem 3 seems to be a little bit more involved and it was kind of different versus what we typically do. But let me go through all of them quickly just in case, okay? The first problem that I noticed actually a lot of you there were two mistakes in it. First of all, for the first problem, all we're using for, so this is problem number 1, is Gauss's law, and Gauss's law really gives us the flux of the electric field over a closed surface. Okay, so the picture there was showing areas, but hopefully you guys through the text actually it tells you that this is actually a surface as shown. So and they should tell you that in the problem that this is a cross section only, so this is basically where the flux of the electric field is. Some of you started doing this integral, which was I was hoping that you should not have done that. But the thing with it is the Q enclosed divided by epsilon naught. A lot of you get it correct, at least they noticed this relationship, but even those who get it correct, instead of dividing by epsilon naught, they were multiplying by epsilon naught. So basically, they were taking the charge enclosed. I don't know, let's take the first one, for example, the first surface, which is kind of easy, because it gives me the charge enclosed basically was what, 6.2 nanocoulombs. For few of you they forgot to, and although the note on the top says, when it was on all of the pages stating that the prefix nano stands for 10 to the power negative 9. So they had a mix of units, and at the end some of you dropped it, which was kind of a mistake because it gave you a value that is totally nonsense for the flux of the electric field. Anyway, some of them were 10 to the power negative 20 and things like that, because this is 10 to the negative 9. And already 1 over 1 over epsilon naught was 36 times pi, 36 pi times 10 to the power 9. So if you have the 10 to the power 9 and then in the numerator, because it's 1 over epsilon naught is 10 to the power 9, and you have 10 to the power 9, so that makes the calculations, all of them is just multiplications of these numbers only. Okay, so that's what the 10 to the power negative 20 was coming from, because you will have 10 to the negative 9 and then you put this one in the denominator. In other words, you were actually multiplying by epsilon naught, you were not dividing by epsilon naught. Obviously, because there were a lot of questions, I mean like what, 1, 2, 3, 4, 5, 6 questions. Since you already made the mistake the first time, that's where you get penalized. So after that, I don't penalize you after that, because I know it's the same mistake that you carried over, because you thought about it once and you didn't think about it correctly, so you lost points for it, and then you copied for the next steps for the other surfaces and you get it wrong. Okay, so that's the first problem. The second problem also was an issue for some of you, actually a lot of you, not some, where they basically give you 2-point charges, Q1 and Q2, and they want you to find the potential somewhere. Okay, and the mistake that some of you did was actually started with the electric field and going through that, and all you have to do is just write the formula for the potential, and the potential is just a scalar, it's a number like 2. Okay, 1 over 4 pi epsilon naught times whatever charge you're considering. I know we have 2 charges, so it's only Q1 or Q2, divided by the distance, okay, of where we're calculating the potential. So all you have to do is just plug in the numbers in here. So I really don't see a lot of thinking in here. Obviously a lot of you get it correct. The second point also the same thing, so 2 points in here, 2 questions related to different points, point A and point B. And then the part that probably got some of you, but hope a lot of you got it correct too, and that is to calculate the work from going from point A to point B. So basically this is what you did. You calculated VA here, you calculated VB in here, and you want to find the work going from B to A or A to B. I think it's an A to B. So in this case the work, no, not, is it the work the question was? Yeah, the work. So the work is going to be the negative of the potential basically. So it's going from A to B, it's going to be Q times What is the question? The work done with the electric current that travels from point B to A. So the final point is the A, so we start from B because of the minus sign. Okay, and that's it. But then you have to be careful with the numbers because this one has a nano in it, again, and this one has 1,000, or the order of thousands, or the end it becomes of the order of 100. The difference between the two potentials. So the expression, instead of expressing in nanojoules, you can express it in microjoules, or you can leave the powers if you wish. Okay, doesn't matter. So in an exam, I'm not too picky about these things. Problem 3 is the one that gave. So I'm going to come back to problem 3. So let me look quickly to problem 4. Problem 4. And that was kind of tricky problem also because of the fact that problem 4 you have a discharge of a capacitor. So they gave you the initial charge, the initial potential. And so the potential at any time t is equal to this expression because this is a discharge, not a charging of the capacitor. Because it has an initial charge, there's no battery whatsoever in the circuit. All you have is just an RC circuit, basically in discharging the capacitor. So this is similar to the lab actually. If you looked at the lab that you did for the charging and discharging of capacitor, the expression that we're using in there is identical. All you have to do is solve just for T, for C in this case, because they give you the V naught. They tell you also V at some time in the future, I think 2.15 seconds. Let's call it T1 for our case in here. And we have R, which is 5.35 mega ohm. Okay, so we have everything in here. All we have to do is just solve for T, and once you find T, which is equal to the negative, C, not T, which is a negative T over R times the ln of the ratio of the final potential, or potential at instant T1 over V naught. Obviously this number is less than 1, so the ln is negative, which cancels this negative, and you're going to find a capacitance of the order of, because this one is of a mega, the answer is going to be of a microfarad. Okay, as a matter of fact, it was so small that it was 0.15 microfarads. I think the correct answer, or 150 nanofarads. Then they ask you to find tau. Once you find what C is, again, some of you made wrong calculations in here, but in calculating C, the tau, it was not really hard to do, so tau is going to be simply RC. Okay, and you have to be careful again with the powers because the order of the magnitude is about a second. As a matter of fact, the correct answer is 0.8 seconds. And then they asked you for the initial charge, the initial energy. The initial energy is simply equal to this case of the capacitor, 1/2 of CV naught squared, since you know what the V naught is, 90 volts, and C is given to you. Is it 90 volts? Yeah, the initial potential was 90 volt on the capacitor. And you have found C from previous steps, so you should have done that. You should be able to get that correct. Anyway, problem 3. And I know I included also the solution, albeit probably it was brief, but it's worth mentioning because it was kind of weird problem a little bit, and that's why I think it upset some of you because of the way that it was kind of different. So we have an EMF in here. So this EMF is given to be 90 volt, and we have a current going through this ammeter that is shown in here. So you have an ammeter in here that registered this current, and this is a 2 amp current. Typically I don't really do a lot of numbers in here when we're discussing problems, but this is worth putting the numbers because you will see something very funny going on in here. So you have a point A in here, and you have a point B in here, and they are connected actually with a 40 ohm resistor. It doesn't matter what resistor you put in there, but for the sake of argument we put in here 40 ohms. Let me tell you why this would not matter. And they show you another EMF in here that they're not sure about its direction, so it's in here that we want to find. And there is actually another resistor here, and that resistor is 22 ohms. So this is basically the setup of the problem. So the first question was to find VA minus VB, because you want to find the difference in potential between points A and B. So in the solution that I provided for you, I created a point in here C, and I said let's find VA minus VB basically by going from this point A to C, then from C back to B. Okay, so in other words, algebraically this expression looks like VA minus VB. So this is a difference in potential between A and B. That one is equal to VA minus VC plus VC minus VB. This together and this together, this is actually, we're going opposite to where the current is through the 45 ohms. So Ohm's law in this case, this is 45 ohms. So Ohm's law in this case says R times I. They give us the current I, which is 2 amps. They give us the potential, the resistor, which is 45 ohms, but we're going against the current, so in this case we're actually rising in potential. So the point C is higher than the point A in potential, and that's what led to this current falling from C to A. So this is actually minus 2 times 45. Plus, now I'm going from the positive side of the battery to the negative side of the battery, and therefore actually this is an actual drop in potential, so the point C is higher than B also by 90 volts. Okay, obviously this whole thing is equal to the difference in potential, and this is where it became weird. This is what really made it difficult for some of you probably to proceed from this point on, because this number was 0. This number is 0. I mean, in the examples we did them before, similar to these problems, is we ended up either with a positive number or a negative number, meaning that either the point A is higher than potential than the point B, or the point B is higher than the potential in point A, and we proceeded there happily ever after because we can find the current that flows. If A is higher than B, so the current will actually rain from A to B. If B was higher than A, then the current actually will rise from B to A. So that's basically what we have. Now we have them both equal. As a matter of fact, the next question asks us specifically which one is higher, A or B. The answer, of course, is because VA minus VB is equal to 0. That means VA is equal to VB. That means there is no difference in potential. Both of them are at the same potential. So what's going on? So there is no current in here flowing from A to B. As a matter of fact, if I want to find that current, I call that I40. So I40 will be equal to the potential difference between A and B, so it's VA minus VB or VAB, divided by that 40 ohms. That's why I was saying the 40 ohms doesn't matter, as long as they have a finite resistor in here. So this is 0, the numerator is 0, the denominator is 40, so the answer is 0. So there is no current flowing through this 40 ohms resistor. So if I apply the Kirchhoff's rule for this node A, for example, I have a 2 amps ohm that comes in here. I have 0 that come out or in, so the 2 amp must follow straight through on this segment, on the segment leading to this EMF epsilon. So there is no current going in and out because of this condition in here, because the 2 points are in the same potential. Okay, so then of course we wanted to find now the EMF. The next question was to find that EMF. So I called this point in the solution D, and I said, okay, so this potential now I know between A and B is 0, so VAB is 0. So what I have in here, I have 0 is equal to VA minus VB, which is actually VA minus VD plus VD minus VB. Again, all I'm doing in here is I'm going through every single point in here for all of the devices. Obviously, if this is the correct direction of the EMF, I'm going from positive to negative, so I'm actually falling in potential by an epsilon value. So this is correct. And then I'm actually falling also because the current in here is flowing from A to D to B. So this is actually the direction of the current. So this is actually D is higher than B. So by 22 times 2. So again, plus 2 times 22. And this must be equal to 0, again, because there is no difference in potential between A and B. So how is that possible? The only way this is possible if the EMF is actually not positive, but rather negative 44 volts. 2 times 22 is 44 volts. So the EMF is actually not in this direction, but rather it's in the opposite direction. So this direction is not correct. So it should really be oriented this way, where the positive in the bottom and the negative in the top. So that's basically what the this means. So the EMF now is negative 44 volts to make this whole thing happen, because there is a drop in here by 44 volts, 2 times 22. So there must be actually a rise in here when we go from negative to positive for 44. Rise by 44, drop by 44, and the two cancel so that there is no difference in potential between A and B. So what's going on in this whole circuit? This is the story then. This EMF, which is 44 volts, is pushing a current which is equal to 44 divided by 22, which is 2 amps. It's pushing a current of 2 amps this way. This EMF of 90 volt is pushing a current which is 90 over 45, which is also 2 amp, and it's also going this way. In this element in here, in this section only, this battery of 90 volt is pushing a 2 amp this way, and this battery of 44 volt is pushing an current of also 2 amps this way. Obviously the two cancel, and there is still no current. 2 amps up, 2 amps down, so there is no net current, and it's still correct. So the whole picture is correct. So both of them are pushing currents in the same clockwise direction. So that's basically how we could register this problem. Had this current, the initial current, the 2 amps, had it been not actually 2 amps, but let's say for example less than 2 amps, then there would be less of a rise in potential in here than this drop of 90 volt. In other words, there will be a point A higher than point B, and in this case there will be a net current flowing down, in which case this current will be less than 2 amps, and this EMF probably need to change its direction, but the value of it will be different than the 44 ohms, actually than the 44 volts. As a matter of fact, it's going to be slightly higher to push this current, and then they combine in there, and it's going to be slightly less, okay, depending on the voltage difference in here. The calculation doesn't matter really, but the point being, in here there will be a net current in here, okay, and the point A will be higher than the point B in voltage. Now if this current was actually more than the 2 amps, then in this case there will be another current. This probably will retain its direction to push more current in this way. Let me try. I'm sorry for that. So this will retain its direction. So this will be it keeps it's the incorrect direction still. So it's going to push more current, and the net current now will be in this direction, because this one will try to push a small current this way, the other one will push even more current that way, and the value, of course, that is going to result from here is going to be greater than the 2 amps. That is the examples that we actually did. Those are the examples we kind of worked with, where the batteries actually, they have a junction and the points A and B were kind of different voltages. Either A was higher than B or B higher than A, but this is a situation that fits in the middle. This is the situation where you guys needed to really overcome that annoyance. Once you saw that, you say, oh, these are the same potential, so no big deal. That is the reaction I was hoping to see from some of you. Anyway, we will discuss more of these problems down the road. We will still have AC circuits, so we'll still have more discussions of similar stuff like this thing down the road. Thank you.